Там закрыть дверь?
Что?
Дверь могу закрыть, чтобы приятно было слышно.
Дверь? Да не важно. Кто-то еще подойдет, может не спать еще. Там всего 4 человека пришло. Звонок был?
Ну, может, 9 на 1.
Еще минуту можно получить. Если я хожу туда-сюда и подойду сюда выпить глоток воды, вы на меня камеру не водите. Все главное на доску.
Ставить, потому что вдруг кто-то медленно.
Да, главное показывать доску все время. Я уж подойду и напишу, что если я куда-то отошел, не надо за мной так сидеть. Я смотрел прежние лекции, так кто-то так делал, это не смотрится совершенно. Да, это неправильный режиссерский прием, вот так вот сидите, потому что не я тут главное то, что вот на доске написано. Давайте начнем. Okay, let's begin this lecture. Hi everybody. Do you like Russian winter? Okay. So, last time we considered a coordinate method to describe motion of the body. Coordinate method consists in choosing some coordinate axis. I have forgotten to take this microphone, by the way. That's it. We have quite forgotten about it. Okay. So, идет звук, да, идет сигнал, слышно? Okay. So we have to choose some coordinate axis, and if these are 2 or 3 axes perpendicular to one another, such a coordinate system is called a Cartesian system. A Cartesian system. And in order to describe the motion, we take the point of interest, the material point A, which we consider, the motion of which we consider, and we have the coordinates of this point, which are functions of time. And so the radius vector that shows by its end the position of the point equals the unit vector I, which looks along the x-axis, times x of t plus the unit vector j that looks along the y-axis times y of t, etc. If there is a third coordinate, then the third term similar to these two ones. So this is a Cartesian coordinate system, and an obvious way to denote the coordinates of the position of a moving material point. There are certainly many other possibilities to choose a system, a coordinate system. For example, there is a polar system which is used very often, and the polar system uses different sorts of coordinates. First, the polar system uses the length of vector r, which may be denoted by rho, for example. And another coordinate is this angle alpha. So if we use polar system of coordinates, then we have to say that x of t will be equal to the distance rho cosine alpha, and y of t will be equal to the distance rho sine alpha. And also, if there is a third coordinate z of t, it will be equal. In polar systems, there is no third coordinate. So the two coordinates which may be taken for a polar system are the alpha and the distance rho. The distance from the origin of coordinates to the point A under consideration. So this is a polar system, polar coordinates. If we need to describe a three-dimensional motion, then we have to add a third coordinate, which is z. And then if we use the polar system, if we use the angle alpha and the distance rho and a third coordinate z, then this will be a cylindrical system of coordinates. Cylindrical coordinates. So apart from Cartesian coordinate system, people use polar coordinates and cylindrical coordinates. And many other coordinate systems are possible. Apart from these three possibilities, there are many other coordinate systems. So if you meet somewhere, if you see somewhere an unusual coordinate system, don't be afraid of it. Just make sure that you understand the connection between the new coordinates, rho and alpha, for example, and the old Cartesian coordinates, x and y. If you have this relationship between new coordinates and old coordinates, then there will be no problem. All the formulas are obtained in a very simple way. So now important definition. Important definition about the degrees of freedom. The number of independent coordinates that you need to describe the motion of a given body is called the number of degrees of freedom of this body. The number of degrees of freedom is the number of independent coordinates that you need to describe the motion of this body. For example, if you have just a material point in three-dimensional space, you need three different coordinates, x, y, and z, in order to define the position of this body and in order to describe its motion. But if you need to describe the motion of this body just in a plane in two-dimensional space, then you need just two coordinates, and the material point will have 2 degrees of freedom. And in three-dimensional space, it will have 3 degrees of freedom. But if you take some solid body, not a material point, but a solid body, for example, if you take this piece of chalk, how many degrees of freedom has this piece of chalk? First, the center of mass will have 3 degrees of freedom. But the motion of the center of mass will not describe the total motion of this piece of chalk, because the piece of chalk may rotate in different ways. So in order to describe rotation along with the motion of the center of mass, we need to introduce more coordinates. So we have 3 coordinates for the center of mass, and then some additional information about the rotation. How many rotations can be introduced for this piece of chalk? 3 different rotations. Along the x-axis, rotation along the x-axis, rotation along the y-axis, that will be this rotation, and rotation along about the z-axis, such rotation. So the solid body may rotate about 3 perpendicular axes. So along with 3 coordinates needed to describe the motion of the center of mass, we need to introduce another 3 numbers, independent numbers, describing the rotation of this body about different, all possible axes. So in order to describe the total motion of this solid body, we need 6 independent coordinates. And so this body will have 6 degrees of freedom. And this kinematical notion is very important in physics, not only in kinematics or mechanics. It's very important in many fields of physics, in thermodynamics and molecular physics, in quantum physics. It's very important. For example, if you have a molecule of water, it looks, if you look at it, it has an atom of oxygen and 2 atoms of hydrogen, and they form some angle. So this, at first approximation, this is a solid body, and so it has 6 degrees of freedom. You need 6 different coordinates to describe the motion of this molecule. But if you take the molecule of oxygen, it has only 2 atoms of oxygen connected in this way, and it's easy to notice that rotation of this object about this axis is actually invisible. It's unimportant. It changes nothing. It's impossible, because the position of electrons is dictated by the laws of quantum physics, and there is no rotation about this axis. So such a molecule will have just 5 degrees of freedom. So this will have 6 degrees of freedom, and this will have 5 degrees of freedom under low temperatures. And it means that in thermodynamics, you will learn later that each degree of freedom absorbs certain amount of energy when you heat the gas by 1 degree. So in order to heat the water vapor, you need more energy than in order to heat by 1 degree oxygen, because oxygen has a less number of degrees of freedom. And if each degree of freedom requires a certain amount of energy, then you need less energy to heat oxygen than the water vapor. But if you increase the temperature to a high degree, then this molecule will become will become vibrating. So vibrational degree of freedom will be released, will be unfrozen, as we say. So in this case, if you increase the temperature, this molecule will acquire additional degree of freedom, and the number of degrees of freedom will rise from 5 to 6 with the increase of temperature. So the very notion of the degrees of freedom is very important in many fields of physics, including thermodynamics, molecular physics, and quantum physics, and quantum mechanics. Yes. So the last thing we considered on Monday was the movement of a material point along a circular trajectory. And now I would like to complete this this topic by introducing the movement along arbitrary trajectory. So suppose we have an arbitrary trajectory along which a material particle A moves. If we take one point on one side of this body A and another point on another side of this body A, then we will have 3 points, and it's always possible to draw a circle which goes through 3 points. You know how to do it, how to draw a circle that goes through 3 points. If we have, I remind you, the geometrical fact, if we have 3 points, we connect the 2 points by a segment and find the middle of this segment and then draw a perpendicular line perpendicular to this segment. And then we repeat the same action with another 2 points and find the middle of this segment and draw a perpendicular to this segment. And then the intersection of these 2 perpendicular lines will give you the center of the circle. And so you're having the center and having the distance. This distance will be the same. This will be the radius. This will be the radius of the circle. If you know the center of the circle and the radius, you can draw a circle from 3 points. So having 3 points, you can always draw a circle which goes through these 3 points. And now if you allow for this point 1 to move closer to point A and point 2 to move closer to point A, then this circle will somehow be deformed, it will be changed, but finally you will have some final position of this circle, the limiting position to which the circle tends when the 2 points tend to point A, when point 2 and point 1 tend to point A. Then the circle will be deformed, and finally it will take some position, which is obviously the circle inscribed into this trajectory curved line, and that will be the best circle fitting the curved trajectory at this point A. And this circle will have some radius r, and this radius is called the radius of curvature of our trajectory of the particle at the point A. And at each point A, at each point there will be radius of curvature of the trajectory. So there will be different radii of curvature at different points. And if we have the radius of curvature and the velocity of our point, we will know the acceleration, the normal acceleration, which is perpendicular to the velocity, and the normal acceleration magnitude will be given as usual for the motion along a circular trajectory. If we have a circular trajectory, then the normal acceleration is the velocity squared divided by the radius of the circle. But now that will be the radius of curvature of our trajectory. So we take an arbitrary trajectory, arbitrary curved line, and we take any point on this curved line, and there is a radius of curvature of the trajectory, which is the radius of the circle that fits the curved line in the best possible way at this particular point. And the formula of normal acceleration of a particle moving along an arbitrary curved trajectory, the formula will be the same as before, as the formula for motion along a circular trajectory. So after this small portion of theoretical information, let's consider a solution of some problems. Let's consider such simple problem. For example, a body is thrown at an angle to the horizon, at an angle alpha, which is 60 degrees, at the initial velocity. Initial velocity is 10 meters per second. And so this body, as you know well, moves along a parabola, and the question will be this: what is the radius of curvature of this trajectory at the upper point? The question is, what is the radius of curvature of this trajectory in the upper point? This is a very simple problem because, as we have just considered, the normal acceleration in this point is given by the relationship, the simple formula, the velocity squared at this upper point over the radius of curvature, which I have denoted by rho, by letter rho. This is a general formula for any trajectory, any curved trajectory of motion of material point. So what do we know here? We know that this normal acceleration is equal to what? Who knows? This normal acceleration is, we know it very well because this is the motion in gravitational field of the Earth. So this normal acceleration is sure to be equal to acceleration of free fall. And also the velocity, it will be horizontal velocity, and horizontal component of the velocity does not change when the body moves, when the body is thrown at an angle to a horizon, because in horizontal direction no forces act on the body. There are no forces in horizontal direction. All the forces acting on this body are directed vertically, and the only force is the force of gravity, gravitational attraction to the center of our planet. And in horizontal direction, horizontally, there is certainly a force of air drag, which we neglect. We think it's small. Sometimes it's small. Sometimes it can be neglected. So we neglect the horizontal force of air drag. And so in this case, the only force acting on this body is the force of gravity. And therefore, the acceleration of this body is the acceleration of free fall, which we know very well. And in horizontal direction, there are no forces acting on the body, and therefore, the horizontal component of velocity does not change. It remains the same as it was in the beginning. And in the beginning, the horizontal component, Vx, was obviously V0 cosine alpha. So the horizontal velocity equals the velocity in the upper point, and it will be the velocity V0 cosine alpha. And from this equation, we easily find the radius of curvature rho. The radius of curvature will be equal to velocity squared divided by g. Well, let's calculate. Velocity squared is this one, V0 squared cosine squared alpha divided by g. That's the final formula for calculations. Well, now we may substitute numerical values for each quantity. V0 is 10 meters, so V0 squared will be 100 meters per second. Cosine of 60 degrees, it's 0.5. So cosine squared will be 1/4. And G, well, approximately 10 meters per second squared. So we have 25 divided by 10, 2.5 in international system of units, meters. That will be the radius of curvature, 2.5 meters. That will be the radius of curvature of this trajectory in the upper point. As far as the units of measurement are concerned, we may check that velocity squared is what? Meter squared over second squared, divided by g, and g is measured in meters per second squared. So second squared will be cancelled, and 1 meter will cancel, and the only thing remaining here is meters. That's correct. So we may check this point, and we should check every time we obtain any formula, we should check it for the validity, if it's valid from the point of view of the units of measurement. We know that the radius of curvature is the distance, and it must be measured in meters, and the formula must give meters, no other unit. So we should check the units of measurement each time we obtain any formula in any problem. Whatever problem you solve, whatever answer you obtain, you must check it for the units of measurement. The units must be correct. If the units of measurement given by this formula, by your answer, turn out to be incorrect, what does it mean? It means that you made somewhere a mistake. It means that there is an error somewhere in your calculations. It's a very good way to check your answer, if it's correct or incorrect. Just check the units of measurements. Also, sometimes and very often, almost every time you solve a problem, it's very useful to check the formula for physical sense. Well, you may imagine, if you increase the velocity, what will happen with the trajectory, and what will happen with the radius of curvature if you increase the velocity or decrease the velocity? If you decrease the velocity, the trajectory will be something like that. It will be smaller, and the radius of curvature must be smaller. It's intuitively understandable. It's clear. It's obvious. So you check the formula. If I decrease the velocity, what will happen to the radius of curvature? Oh, good. I understand intuitively that the radius of curvature should somehow be proportional to the velocity. The smaller the velocity, the smaller the radius of curvature. That's good. That's intuitively understandable. And also the acceleration of free fall. Suppose we carry out this experiment on the surface of some other planet where the acceleration of free fall is different. It differs from the Earth. So on the Moon, it's 6 times less. It's 6 times smaller on the surface of the Moon. If the acceleration of free fall is smaller, then the body would fly somewhat farther, and the radius of curvature would be much greater. It's intuitively understandable. So if g is allowed to diminish, then the radius of curvature should increase. That's what we observe from this formula. The radius of curvature is inversely proportional to acceleration of free fall, and that's reasonable. We understand it's by intuition that what should happen if we repeat this experiment on the surface of the Moon or some other planet. Or if the acceleration of free fall is very large, then the body would not go far, it would fall immediately. If the acceleration of free fall is very large on some planet, much heavier than Earth, then the radius of curvature would be smaller. That's okay. If the denominator grows, then this quantity will be diminished. So checking the answer for physical sense is very important. Always, in every problem you solve. Every formula you obtain in your life, every formula should be checked for reasonableness, for physical sense. It should comply with your intuition. Certainly, sometimes our intuition fails, especially in the field of quantum physics. And then you obtain formulas which seem to be absurd. But what will be the final check for the validity of this formula? The final check will be the experiment. And if the experiment confirms the formula, which is against our intuition, if the experiment confirms it, and not a single experiment, but dozens and hundreds of experiments carried out in different laboratories by different groups of physicists, then the formula should be considered correct if it complies with the experimental results. Then the formula is correct even if it goes against our intuition. Sometimes it happens, especially in quantum physics. But mostly, in most cases, in classical physics, our intuition works well. It works, it confirms correct formulas are in compliance with our intuition, especially in the field of classical mechanics. However, there are such situations when I showed you the experiment last time when the gyroscope axis was followed the curved metal surface. That's also difficult to understand at first sight. But then, when you learn more about gyroscopes, you will develop your intuitive understanding to such an extent that you will well predict the result of such an experiment. It will be in compliance with your intuition. But in order to achieve this level of understanding, you must work individually and develop your understanding and your intuition. Okay, let's consider some other problem. Number 1.19. I will solve problem 119 from Irodov collection of problems. Well, problem 1.19 says, a point traversed half a circle of radius r, radius is given 160 centimeters. A point traversed half a circle of a given radius during a given time interval, 10 seconds. During a given time interval of 10 seconds. Calculate the following quantities averaged over that time. We have to calculate the mean velocity. We have to find the mean velocity. The mean is denoted by such brackets in physics and mathematics. Sometimes there are also other possibilities to denote the mean value, but this notation is used in this problem. So we have to find the mean velocity, the modulus of mean velocity vector. So when I use the symbol of velocity without vector, it means that I consider just the quantity, just the magnitude of velocity, paying no attention to its direction. But when I consider the velocity as a direction, as a vector, I certainly use the symbol with a vector. And in printed version, they use the bold character. The bold character means that this is a vector. So we have to find the modulus of the mean velocity vector. We have to find the mean velocity vector and its modulus, the magnitude. And then we have to find the modulus of the mean acceleration. Acceleration in this book is denoted by omega. Strangely enough, I don't like it, but I can do nothing. I cannot change it. They denote acceleration by omega. If the point moved with constant tangent acceleration. That's the whole statement of the problem. So a point moves along a circular trajectory. We take a circular trajectory, and it says that the point traversed half a circle, just half a circle. This is the center, and the point started here at A and ended at point B, and so it traveled along this circular trajectory. The radius is given. The radius is given. And it's known that some material point went from initial position A to final position B along this curved circular trajectory in 10 seconds, in time tau. And it's known that the point moved with constant tangent acceleration. And under these conditions, we have to find the answers. What is the velocity if we don't speak about the vector, about the direction of velocity? We may call it speed. What is the speed of a particle, of a point? What is the definition of speed? The definition of speed, this is a physical quantity which has its definition. And the definition of speed is what? Path covered by a point divided by total time of motion. So, the mean speed is the total path divided by total time. Total path is what? It's the length of this trajectory, and the length L is pi r, because the total length of a circle is 2 pi r, and we have just half a circle, which is pi r. That is the total length of the particle path. So this will be pi r divided by total time, which is given. It's tau. So what is it? 160 divided by 10, 16 times pi, 3.14 times 16 centimeters. That will be about 50 centimeters. About 50. 5-minute interval. You don't have to be seated. You may stand up and go around and have a rest for 5 minutes. continue our consideration of this problem. The first question, what is the mean velocity or mean speed? The first question can be solved in this way. It's very simple. So what is the second question when we need to find the mean of the vector of velocity, taking into account its vector property? So what is the definition? When we were not interested in vectors, we took the total path and total time, and we don't consider the form of this trajectory. The trajectory could have been different. It could have been a straight line, or it could have been, the trajectory could have been something like that, or anything. We needed just to know the total path covered by the point. But here, the form of the trajectory plays its role because we consider the vector of velocity. And so if in the first question we considered just the total path, in the second question we must consider the total displacement, because the displacement of a point from its initial position to its final position is a vector. That is the vector of displacement, AB. And so in this case, in the second question, we have to consider the total displacement over total time. And total displacement is a vector quantity. So whatever the trajectory, whatever the path, it could have been different paths, but the total displacement, that's what is important here. In order to find the mean vector of velocity. Each moment of time, vector of velocity could have different direction, but the total displacement is some characteristic of the mean motion, mean direction of motion. So we have to take this quantity, and total displacement equals 2 radii. It's 2r, the diameter of the circle, divided by the same time interval tau, which is what? Very simple. 2r is 320 centimeters divided by 10 seconds. That's it, 32 centimeters per second. 32 centimeters per second is just the magnitude of our vector. It's just the magnitude. And that's, by the way, what we need to find in this problem. We need to find the magnitude, the modulus of this vector. So I started from considering the vector, but finally I go to what the problem requires. I return to the modulus of this vector, so I put the sign modulus, and here I have just the modulus, just the quantity. Yes, what's the question? Sorry, in this case? Oh, yes, sure, you're. Oh, no. We divide by 10. We divide by 10 seconds. Oh, sure, second is here. Yes, sure, yes, you're right. Thank you. That's correct. Thank you. So, we have found the mean velocity, which is 50 centimeters per second, and the mean vector of velocity, which is 32 centimeters per second. Very different things. And now, suppose that the trajectory is such that point B coincides with point A. The trajectory is closed suppose the point started here and after traveling along some trajectory ended at the same point. What will be the path in this situation? The path covered will be the length of this trajectory, which should be substituted here in the denominator of this formula. And what is the displacement in this case? 0. So in this case, the mean vector velocity would be 0 if the trajectory was closed and final point coincided with the initial point. Then we would obtain 0 here. That should be understood. And these quantities are very important in which case, in which situation. For example, when we consider diffusion of particles. Diffusion. In diffusion, the particle goes through very complicated trajectory as a Brownian particle in diffusion. Very complicated trajectory, and the path covered may be very, very long, but the displacement is very small in diffusion. The Brownian particle moves chaotically to and fro, and it covers thousands of meters, but the displacement may be just a few millimeters. So these two quantities would be very different, would have very different values by the orders of magnitude. They would be different by the orders of magnitude because the total path may be very large for a Brownian particle in a Brownian motion in diffusion, but the total displacement may be very small at the same time. And now we have to find the answer to the last question. We have to find the mean vector of acceleration. So again, I start from the vector of acceleration. And the modulus, I will take the modulus later. The vector of acceleration. So, if we compare the vector of velocity and vector of acceleration, the definitions are similar, with the only difference that in velocity we consider total displacement, that is total change in coordinates of the point A. And in acceleration we consider total change in velocity. That's the only difference. Here we had total change in coordinates, which is A from coordinates A to coordinates B. That was the diameter. And here we must consider total change in velocity. How to consider total change in velocity? We must know the velocity at the initial point, v0, for example, vector, and the velocity at final point, v final vector. The velocity is always directed along the tangent to the trajectory, tangential line. This is a tangent to the trajectory. So in the beginning, the velocity vector is directed upwards, and in the end, the velocity vector is directed downwards. It's a tangent to the trajectory. But we don't know the magnitude of this vector. We know nothing about the initial velocity and nothing about the final velocity. The only thing is given in this problem is that the motion was at constant tangent acceleration. That's the only thing we know. Okay, in order to solve this problem, let's first consider the simplest case, when the tangent acceleration was 0. It was constant, but it was 0, or very small. So that the initial magnitude of velocity equals the final magnitude of velocity. The velocity did not change. We assume this situation. It does not contradict the problem. The problem says the acceleration was constant. Okay, we consider the particular case of constant acceleration when it's 0. It's constant. It's 0. So the initial velocity length of this vector equals the length of final velocity. And in this particular case, the simplest case, we start solution of problem from consideration of a simplest possible situation. It's always very, very useful to consider first some particular case which is simple, and then we generalize this case to a more complicated situation. That's very often way of solving very usual method of consideration of different problems. First, we consider the simplest thing. And so we have to find the total change of velocity, of vector velocity. That is the final velocity minus the initial velocity vector, divided by total time again. If the velocity was constant, then the final velocity is just minus the initial velocity. The vector is the same in magnitude, but oppositely directed. So final velocity, I take it into account, that's a vector of final velocity equals minus vector of initial velocity. Or initial velocity is minus vector of final velocity. So it will be 2 vectors of final velocity over time. And final velocity is the same as initial velocity in this case, and the velocity is constant because we assume the acceleration was 0. So in this particular case, it's very easy to find the velocity, not a vector. Vector quantity, look here, where is this vector directed to? In what direction? What is the direction of this vector? We see that the direction from here, the direction is downward. Downward, because from the vector directed downward, we have to subtract the vector directed upward. It means we have to add the vector directed again downward. So the total direction is double the final velocity. The direction is known. And now if we go from direction to the magnitude, then we have to find the magnitude of this vector of velocity. It's very simple. We have to take the whole path divided by the total time, which we already know. What is it? This quantity is the velocity, mean velocity in this case. So the formula will be 2 pi r divided by tau. That is the magnitude. I started from consideration of the vector quantity, and then when I understood where is the direction, what is the direction of this vector quantity, after I have understood it, I forget about it, and now I consider the quantity, the magnitude of this vector. Well, the formula is very simple, 2 pi r over t. That will be over tau. That will be twice this magnitude. 2 pi r. Oh, no. That is only the pi r over tau. That is the velocity. We have to multiply by 2, that is, and we have to divide by tau. So there is another tau here. I have forgotten about it. I have taken this formula pi r over tau, and then I have to divide by another tau. That gives me tau squared in denominator, and I have not to forget about this coefficient 2. That's the final formula for the mean vector of acceleration in this problem. And the calculation will be very simple. It will be 50 times 2, 100 divided by tau, which is 10. That will be 10. 100 divided by 10. That will be 10 meters per second squared. That will be the mean vector of acceleration in this particular case. So, this problem seems to be in your homework. It belongs to your homework, yes. 119, this problem is from your homework. You were supposed to carry out this solution by yourself. I have solved it for you. I have solved everything except the last step. I found this vector, mean vector of acceleration, in a particular case when the acceleration is constant but equal to 0. I suggest that you finish this problem at home and find the final answer in general case when the acceleration is constant but not 0. Just make this final step by yourself at home. I may suggest that the answer will be the same. The answer will not be changed. But you will have to prove it yourself, that if you take into account the constant acceleration along the path, the tangent acceleration, the answer will not be changed. It will not change the answer. So just make this final step at home, because this problem is a part of your homework. And we now consider some other problem. Let it be 122. Let it be problem 122. Problem 122 says, the velocity of a particle moving in the positive direction of the x-axis varies as, so the velocity of a particle is given, it varies as some constant alpha square root of x. Alpha is a positive constant. Assuming that at time moment t equals 0, when t equals 0, the particle was located at the point x equals 0. So at the initial moment of time t equals 0, the particle position was at the origin, at the reference system origin, x equals 0. So that is what's given in this problem, and what is the question? We have to find the time dependence of the velocity and the acceleration of the particle. So we have to find the function v of t, the time dependence of velocity, and we have to find the function acceleration of this particle as a function of time dependence of acceleration. And the mean velocity of the particle averaged over the time that the particle takes to cover the first s meters of the path. Okay, that's later. First let's find answers to these two questions. So it's known that the velocity of the particle depends on its coordinate x. Whatever coordinate x, the velocity is known. At every position, we know the velocity. At every position of the particle x, we know what the velocity will be at this point. And we have to find the function v of t. We are given the function v of x. This is the function v of x. Velocity as the function of the position x. And we have to find the function v of t. Velocity as the function of time. How can we do it? There is a similar problem in your home assignment. A similar problem. How can it be done? Very simple. We have to remember, we have to recall what is the velocity. By definition, the velocity is a time derivative of coordinate. So to put it in simple words, it's delta x by delta t, which in physics is denoted as dx by dt, the time derivative of the coordinate. That is the definition of velocity. And by using this definition, I will take this part of the formula and this part of the formula. And we can write that dx by dt equals alpha square root of x. In this equation, we have x, the coordinate of the particle, which is a function of time, because the particle moves, and the coordinate x changes in time. And also we have the time derivative of the function. So we have an equation when we have an unknown function x of t and its derivative with respect to time t. Such an equation is called a differential equation. And there are many, many different kinds of differential equations in physics, and a lot of possible methods to solve such differential equations. In this particular case, the solution is very simple. We have to separate the variables. The variable x should be all taken in one part of the equation and the variable t in other part of the equation. Then we obtain here dx divided by square root of x equals alpha dt. So I divided the equation by square root of x, and I multiplied this equation by dt. I obtained alpha dt. So all the x variables are concentrated in the left-hand part of this equation, and all the variables associated with time are concentrated to the right side of the equation sign. Now we have to do what? We have to integrate this equation. What is to integrate? To integrate a function, it means to integrate function f of x dx. We have to find another function, capital F of x, such that if you differentiate this function with respect to x, you will get small f of x. So integration is antiderivative. Integrating a function it means that we have to find the antiderivative, because the opposite or the reverse operation is differentiation. To find the derivative, if we differentiate this function capital F with respect to x, we must obtain the function which is here under the sign of integral. That is what integrating is. I don't know whether you studied this in calculus. Not yet, I suppose, but not yet. Okay. And do you know how to differentiate functions? Have you studied differentiation? Okay. So integration is the reverse operation, and the meaning of integration is here, nothing more to it. There is nothing more, just to find the reverse operation, which is reverse to differentiation. So we have to integrate this equation. It's very easy to integrate dt, because alpha is constant. It can be taken out of the integral sign. So I will show you in detail. Integral of alpha dt equals alpha integral of dt, because alpha is constant, and constant can be taken out. Integration is certainly kind of denoting a summation. We have to find a sum of this function f of x in many, many points x, in many different points x. So this operation is to find a sum, a certain sum. And if we have a constant coefficient in each term of the sum, then this constant coefficient we may factor it, we may take it out of the sign of the sum. And so we have to integrate only this equation, only this function. And what is the function under the integral sign? This is just 1. This is just a unit which stands here. And what should be differentiated in order to obtain 1? What should be differentiated? So alpha remains on its place, and what should be differentiated? Just t. If you differentiate t with respect to t, you obtain 1. Is it clear? Because t with respect to t equals 1. So to take the integral, this integral is a very simple procedure. It's just alpha t. Certainly we have to take into account that this is an indefinite integral, and there should be some indefinite constant. We don't know any constant should be added here, because if we differentiate a constant, then we obtain 0. If you differentiate a constant with respect to t, you will get 0. So any constant can be added here, and that will be correct. Any constant can be added. And now let's pay attention to another part of this equation. So we have considered the right-hand side part of this equation. This turns out to be alpha t plus some unknown constant. We will find it later. And another part of the equation, we have to take the integral of this expression. In this particular case, the function f of x is what? Is 1 over square root of x. 1 over square root of x. How to find the function which, after being differentiated, will give us 1 over square root of x? I will give you a formula. X to the power of n dx is x to the power of n plus 1 divided by n plus 1. That's the general formula to integrate. Because if you differentiate the right-hand side part in this equation, if you differentiate it with respect to x, if you try to find the derivative of this expression with respect to x, what will you do? First, you will have a coefficient n plus 1, which will cancel with the denominator, and then you will have just x to the power of n, the function under the sign of integral. So that's the general simple formula to find such integrals. And in our particular case here, it will give us, in this case, x is taken in the power of minus 1 over 2, because square root of x is x to the power of 1 over 2. And 1 divided by square root of x is x to the power of minus 1 over 2. In our case, n equals minus 1 over 2. So using this formula, we will obtain here square root of x. If you substitute here instead of n, if you substitute minus 1 over 2, in our case this is minus 1 over 2, then in our problem we will get x to the power of 1 over 2, 1 minus 1 over 2, divided by 1 over 2, divided by, what is it? 1 over 2. So that will be 2 square root of x. If you differentiate this expression with respect to x, you will obtain the function which is found under the sign of integral. Just take the derivative of this and you will obtain square root of x in the denominator. So all this mathematics lead us to final expression, which is 2 square root of x from the left-hand side integral should equal to alpha t plus unknown constant c, which we have to determine now. How can we determine it? It's known that when time equals 0, coordinate x must also be equal to 0. It's given in the problem. So if we substitute 0 here and 0 here, according to the statement of the problem, we must obtain equality. It means that identity. We must obtain identical expressions. So this unknown constant necessarily equals 0. It should be 0. Because if we substitute 0 here and 0 here, this equation should be satisfied. This can be satisfied only if the unknown constant is also 0. So this condition given in the problem, that the coordinate of the particle is 0 when time is 0, this condition helps us just to determine this indefinite constant. We have found it. It must be 0. So the final equation shall be 2 square root of x is equal to alpha t. How can we find, what can we find from here? We can find function x as a function of time. We have to find the square of this equation, and it will be what? Alpha squared t squared over 4. We have found x from the first line. X, that will be alpha squared t squared divided by 4. So this is time dependence of coordinate x, of our moving point. If we know time dependence, we can easily find the velocity, because the velocity as a function of time is just the derivative of x with respect to time, and we have to differentiate this function with respect to time, and it will give us alpha squared divided by 2 times t. That is the time dependence of the velocity, the answer to the first question of our problem. By differentiating the coordinate with respect to time, we find the velocity. Why? By definition of velocity. Velocity is defined as dx over dt. Dx over dt is denoted in physics and mathematics sometimes as x prime t. So this is the same as writing dx over dt. These are just different notations of the same thing. In order to find the velocity, we have to find dx over dt. We have to differentiate x with respect to time. Function x of time is known. How to find the derivative of this function you should know. So we have differentiated this function and we obtain the answer for the velocity. Now, how can we obtain the answer to the second question? How can we obtain the acceleration as the function of time? Well, again, in order to find the acceleration as the function of time, we have to use the definition of acceleration, just the definition. And the definition is derivative of the velocity with respect to time, dv over dt. And what is velocity as a function of time? Yes, we know it. We have just found it. We have to find the derivative of this function with respect to t. It will be just alpha squared over 2. That's the derivative of this function. So we have found that the acceleration is constant. It does not depend on time. Acceleration is constant. And certainly, as we know the acceleration, we can present this formula as the well-known acceleration times t. The coefficient turns out to be the acceleration. Acceleration times t is the expression for the velocity when the acceleration is constant. The velocity of particle is at. You know very well this formula. And the path covered by the particle is given by a simple formula, which is acceleration times squared over 2. That is also obvious from the previous expression. As we know what is the acceleration, we can substitute it here and find that the particle coordinate turns out to be at squared over 2 with the acceleration a equal to this expression. And this is the well-known formula for uniformly accelerated motion. That's it. We obtain what we know very well. In other words, what we have obtained by solving this problem turns out to be very well-known formulas, very well-known results from previous semester. Any questions? So I wanted just to ask you, what about calculus? Do you have lectures in calculus? And did you have these lectures last semester? No, calculus just started this semester, right? No? Last introduction to calculus. So you consider derivatives and differentials. So you know how to differentiate functions. Okay, that's what you need. If you know what is the sine omega t derivative with respect to t, if you know that this is omega cosine omega t, then that's practically all you need to solve problems in your home assignment. You must be able to differentiate functions, simple functions like sine, cosine, t squared, square root of x, well, just simple functions. That's all you need to solve the problems. The only thing you need to understand is the method of solving. The method of solving in many problems in your home assignment is to obtain a differential equation like this one, and then to integrate it. To integrate is to find a function which is antiderivative. The reverse operation, reverse to derivative, to finding a derivative. That's it. That's all there is to it. So on this point, let me finish this lecture. I think it's, is it the time? About the time. No, it's in a minute we will have it. Через минуту будет этот звонок, да? Я уже все, больше ничего не успею рассказать.